Howdy, Huskies. Welcome to Unit 2, aka Chapter 3. Mr. Naughton here, the color guy. We are going to go ahead and get started talking about our exponential functions, which is going to be basically just when our x is in the exponent. Before we dive too much into that, though, I got some review questions for us. So please go ahead and pause this, try those review questions, and then we'll go over it, make sure we're great. Multiplicity. Remember, multiplicity is how many zeros we have at a given zero, which in this case is 9. So I'm going to focus in on just that part, because that's the only time when we solve this, I'm going to get x equal to 9. So how many of those do we have? We have 5 of those. So the answer here truly is 5. Alrighty, let's erase that so we can focus in on number 2. What is the end behavior here on number 2? Our end behavior is what's going on as our function really kind of leaves our field of view. So for that, we're going to look at our leading coefficient and our degree. So since this bad boy is going to be a positive leading coefficient and an odd degree, that means that they're going to go in opposite directions, and one's going to start low and one's going to end high. So you can write your end behavior in the easy one, which is starting low, ending high, or the ever classic as x approaches negative infinity, which is our left, and then positive infinity, which is our right. What is the function doing? So let's go ahead and write that really quickly. So our left arrow is obviously down, so negative infinity. Our right arrow is clearly going up, so that's positive infinity. Easy peasy lemon squeezy. Cool. And last but not least, we're talking about real positive zeros. We bring this up because there will be times where we still need to solve for x. So we got to keep those zeros in check. So we're going to go ahead and make sure that we are doing our Descartes rule of signs here. So this is a positive. So we're looking for positive changes. So I went from positive to negative, so that's 1 sign change. Negative to positive, 2 sign changes. Positive to negative, 3 sign changes. So we had 3 sign changes. So we think our answer is just 3, but remember they come in pairs. So it's going to be 3, or it's a possibility of 2 less, which is 1. So there's our answer to our review questions. Alrighty. Time to get in the nuts and bolts of what we're chatting with today, which is exponential functions. Cue the applause. That's not my highlighter. There we go. So an exponential function is when things are going to get either really, really big quickly or really, really small quickly. Okay? There are a couple parameters. It's got to be a non-negative real number. So the idea is there's no decimals. Okay? There can be, I meant to say there's no negative numbers. Decimals are okay. Again, non-negative means no negative numbers. Decimals are okay. But there is one number we don't want to deal with, and that's right here we're going to talk about, and that's what happens when b is 0. Well, if we think about this, if I make this a 0 to the x power, what's going to happen? It's going to turn to 0. So that means it would turn into a constant graph or a constant function, depending on whatever is going on else with that. Okay? So we don't really want to deal with that. So it's completely different. So we're looking at just b to the x. All right, so a couple things we need to remember from Algebra 2, because we did talk about this in Algebra 2. When b is greater than 1, that is our growth factor. It's going to be known as growth or increasing. I call that when it's taking off. So it starts real low and then explodes up like it's taking off. When it's in between 0 and 1, now again, it's never going to be negative, so we don't want to say it's a negative one. And then our b, again, as I goofed and I apologize earlier, it can be a decimal because these are times it will be a decimal or a fraction. This is going to be known as decay or decreasing. So I call this one landing. So landing would mean start high, and then it's going to sort of level off and land on your asymptote. It's not going to actually touch it, but it's just a different way to think about it. All right. Now, we're going to call this our crucial point, is our y-intercept of 1, because b to the 0 is always 1. Okay? Anything to the 0 power is 1. So that's going to be an important point for us to use. We're going to talk a lot about asymptotes. So remember, as we talked about in the last unit, Asymptotes are going to be lines the graph approaches and rarely cross. And the reason why we're going to have an asymptote is because there's no power of x that's going to give me 0. Okay? So our shifting rules can apply, and we're going to investigate that, but it can look like this. So this is our shifting rules. So we're going to have an h, and notice it's a minus h. So that's going to be opposite. And then our k is going to be really important because eventually we're going to see that that's going to shift values up and down as well as our asymptote. And then we could also have a stretch with our a. Cool? So our domain and range, talking about this in brief terms, our domain and range is going to be all real numbers. So negative infinity to infinity, because there's going to be no holes in our graph. And our range is either going to be y is greater than k or y is less than k, depending on what's going on. Cool, and we'll get more into that later. So it says, with our directions here, it says want to make a table and check it on the graphing calculator. So get your graphing calculator handy, like what we have right here. Okay, so you can do this as well. But we're also going to start with the table. And the reason why we're going to start the table is it's best to know why the graph is the way it is. So I'm going to have 3 functions. I'm going to have my first one, which is y to the 2x. Then the green one is going to be a negative x. And then last but not least, a negative 2 to the x. Okay? So we're going to talk about all 3 of those different ones so we can see really what's going on with our b and our a if we look at this transformation equation up there. So I'm going to make my table, and to make this short and sweet, these are always going to be my x's, and then we'll do -3, -2, -1, 0, 1, 2, and 3. And then to match up my colors, this will be my 2 to the x, this will be my 2 to the negative x, and then this will be my -2 to the x. Okay? So, ladies and gentlemen, let's jump into 2 to the x. So, the idea of this function here in blue is that it is doubling every single time. Okay? So, let's start with, and this might be a little bit funky, but bear with me here. We're going to start at 0. Okay? So, what's 2 to the 0 power? Anything to the 0 power is 1. Then 2 to the 1 would be 2, 2 squared would be 4, and 2 cubed would be 8. Okay, so 0, 1, 1, 2, then 4, 8, sorry, 2, 4, excuse me, and then 3, 8 off our graph. So you can see the rate of change here is really getting very, very quick. Alrighty? So let's look at these other values, and we're going to look at them secondly, because we have to remember an important rule is that negative exponents are going to actually flip your b. So for this one, it's going to be 2 to the -1. That's really going to be the same thing as 1/2. Because it really is 2 over 1. We flip it, so it's 1/2. Not going to work. So then this will be 1/4, and this will be 1/8. So you can see that those values are just going to get really, really close to our asymptote there at 0. Hence why we said our asymptote is going to be at 0 when we said our horizontal asymptote. So if we graph this, it's going to look something like this. Cool? So that is our basic exponential growth with a growth factor of 2. And we can see how it's getting very, very quick. Alrighty, so let's do our next one here. I'm going to put it on the same graph so we can compare. Now notice that's a negative x. You with me? So let's think about this. You have to do your exponents first. So I can't just do 2 to the number and then flip it. I got to actually make this really 1 over 2 to the x. Okay? So we have to take care of that negative exponent first. So that means that this is going to be 1, because we said anything to the 0 power is 1, 1/2, 1/4, 1/8. Well, then if we look up top with the negatives, those are double negatives would be positive. So this would be 2, 4, and 8. So as we can see here, this is going to be still at that same crucial point, 0, 1, as we mentioned above. Then it would be negative 1, 2, 2, 4, and then 3, 8. And then these would be boom, boom, right against our asymptote. So if we look at that, sports fans, we're going to have a graph that goes like this. So you can see the difference between this would be a growth function and this would be a decay function. We see that decay function because our growth factor became, as mentioned down here, 1/2. So anytime it's between 0 and 1, aka 1/2, that's why it's decay. Looks different. Now, last but not least, okay, we're going to have this negative 1. So I'm going to switch to my pink here. Now, we're going to go, this is really the same thing as saying a negative and then 2 to the x. And the reason is that we have to think about it that way is, once again, our PEMDAS. Now, this is what students are going to have a tough time with, and that's why we're going to take special attention here to make sure we're good. Going back to PEMDAS, we'd have to do our exponents first, okay? So our exponents first would be 2 to the x because there's no parentheses right there. So that's why we're going to have it negative 2 to the x. So basically, it's going to be the same as our blue one, just everything is going to be negative. Negative 1/2, excuse me. Negative 1, 1/2, 1/4, 1/8. So if I plot my points, it's going to be clearly a mirror image, but it's going to be underneath. I don't really have a lighter pink. Good thing I can make one. There we go. So you can see, ladies and gentlemen, that it is exponential growth because it's going away from your asymptote. It's just going in the negative direction. So once again, I'm going to call this one growth. Cool? Alrighty. So, ladies and gents, let's mosey on over to example 2. On example 2, we're going to investigate the ideas of our H and our K. Alrighty? So this is where we really get into our domain and range here. Okay? So, ladies and gents, let's do our first one here in blue, and then we'll do our second one here in red so we can see what's going down. So let's go ahead and look at this. So 3 to the x means it's actually tripling every single time, okay? But since we're doing +1, that's actually going to mean that it's happening earlier. We're going to move it to the left 1 unit. So if I were to make my normal table, your XY table, notice we're just doing this for the blue, 0, 1, 2, and 3, I'm going to just use those values rather than having to do all those negatives again, because I know it's just going to get really close to my asymptote. So this would be anything to the 0 power is 1, and then this is going to be 3, 9, and then 27. So this was just, again, 3 to the x, but it's 3 to the x plus 1, okay? So we're going to do our opposite because notice our transformation equation, it's a negative h. So I'm going to go ahead and say it's going to get there faster. So I'm really going to subtract 1 on all of my x values. So this is negative 1, 0, 1, and 2. And we'll just cross those out. So as we can see, I'm at now negative 1, 1, boom, then 0, 3, then 1, 9, and then I'm not even going to bother with the 27. So you can see that that shifted the graph over to the left 1 unit. So our H is still left and right shift. So then let's look at our K value. Now notice this K value, that plus 1 is after our exponent as opposed to with it as we saw previously. So that means when I do this one, x, y, my k is going to affect the y. So I'll do 0, 1, 1, 3, 3, 9. I meant to 2, 9, 3, 27. There we go. And then I'm going to add 1 because our k is the exact value. So this is 2, 4, 10, 28. So boom. And then 1, 4. There we go. And then way off. So this is going to be the up 1. So I'm going to start up above that and go up. So we clearly see here that not only does this shift it up, but it's actually going to go ahead and shift our asymptote as well. And the reason is that even if we pick something like -3, -3 would be 1 over 27, but I'd still have this plus 1. So it'd be technically, to make a bad mixed number, 1 and 1 over 27. So it's still going to be above that asymptote at 1. So that's why it's going to move everything up 1. So let's go back up here. So this is going to be our left and right. And as mentioned, the k is going to be up and down, but it's also going to move your asymptote as well. You good with that? All righty. So ladies and gentlemen, let's go ahead and play with these two to make sure we know how to plug them in our calculators correctly. So I have my calculator out here, turn it on, go to y equals, and then I'm going to go ahead and do 3, and then right above the divide sign is the upper arrow, it's known as a caret. So notice I have x plus 1 where it is actually above in our exponent. And then in my next one, I'll do 3 to the x. And then I'm going to hit the over arrow to bring that back down and do plus 1 so we can see the difference. So we're going to see one where it's going to be a little bit to the left and one where it's going to be a little bit above. Boom, shakalaka, there we go. Just basically like we showed. Groovy. Okay? So, ladies and gentlemen, super great, super awesome. Calculators are fun. Okay? Now, it's important that you know how to graph this by hand and a calculator because there will be a non-calc and a calc version of your next test / celebration of knowledge. Okay? So, calculators important. Also important to be able to do it by hand. Alrighty. So, let's investigate this straight up because we only have one example here. How would we do this one? Okay, just looking at it. Well, the first thing I would recommend you do is look at your B value. So that is in between 0 and 1. So I know that this is decay. You good with that? So I also know, I should just make it look like decay. And then I will also mention that this is 2.4, 2.5. That is your asymptote. So I could go ahead and just draw that right away and go, all right, so this is 0, 1, 2. I know where my asymptote is automatically. Cool? All righty. So for growth, if we go to the previous example for a moment, I used 0, 1, 2, and 3 because those were my easy answers. For decay, I'm actually going to say -3, -2, -1, 0. Because I know that's going to flip that 1/4 to the x power to eventually make it 4 to the x. Okay, and that's easier to me. So 64 is going to be 4 cubed. 16 is 4 squared. 4 to the 1 is 4. Anything to the 0 power is 1. And then again, we are adding our k value to that. So this is going to be 66.5. 18.5, 6.5, and then 3.5. We good with that? Alrighty, I need to pause and answer that phone as you can hear it ring. Alrighty, my phone is no longer ringing, so we are all good. Lost my train of thought, so here's what we're just going to go ahead and tell you. What you're going to do is remember our critical point was at 0, 1. Okay? So that was because anything to the 0 power is 1. So what you're going to do is you're going to go basically to 0, 1. And I just put a small dot right there. And then apply your vertical shift, in this case, where your asymptote is. So I would go up from there 2.5. So this is where the actual graph is going to cross. So that's your crucial point. And then from there, you can either use your points or you can just go your growth factor, 1, 2, 3, 4. Back 1 because we know it's decay, not over 1 because it's growth. And then boom, shakalaka right there. If we are graphing it by hand, you basically need your asymptote, your crucial point, and one other point to make sure we understand what's going on and you're good to go. Okay? So if we put that in the calculator, just to make sure we're all good, the reason why we want to make sure we do this in the calculator is you put that 1 divided by 4 in the parentheses. You always have to do your growth factor in parentheses when you do it decay, or when you have decay, or else it's going to show up something very funky. Boom, just like we had it, just like we drew it up. Except my 2.5, it was a little off because I put in a times instead of a add. There we go. Much better. Helps if you put in things calculator correctly. Cool. Alrighty, so let's speed up this process because the last couple of examples have taken us 20 minutes. How do we do this quickly? So, again, you're looking at this growth. Take the 4, that's growth. Find your asymptote, put that in right automatically. You good with that? Everybody gravy? Alrighty. So, normally 0, 1 is going to be your critical point. Okay, so your critical point, again, where your B would equal 0, I'm going to shift it down 1, and then plus 2, I'm going to do the opposite of that, so I'm going to go over 2. So this is my new critical point right there. So then the growth is 4, so I would go over 1, up 4. That's your second point. Erase all this other stuff. Let me see if I can hit those a little bit better. Lord have mercy, you guys hopefully get the point. There we go. Cool with that? And let's follow directions for once in our examples here. Our domain is negative infinity to infinity, and that's always our domain. And then this, because it's above, is going to be y is greater than a negative 1, or from negative infinity to negative 1. And then no brackets, because it's never actually going to hit our asymptote. So, to recap that last one quickly, because this is the way we want to do it, do your asymptote first. Step 2 is our critical point. I'll just put our CP. That originally was 0, 1. Then you're going to move with your asymptote, which is why we went down 1. Okay. Then go over with your H. Remember, that's opposite, so that's why we went over 2. And then that's your critical point. And then whatever your growth factor is, you go over 1, up 4, because it's growth, and if it's decay, you go back. Easy peasy lemon squeezy. Alrighty. So what happens a lot with our growth functions and our decay functions is what happens when we start looking at this natural base E, something we're going to be talking a lot about in the next couple of weeks. Okay? The natural exponent function, as we see right there, is used a lot in chemistry and to solve decay problems. Kind of like half-life stuff. Super important in chemistry. Where E comes from is if you take that 1 plus 1 over n to the n, and we'll talk about that in just a hot second, and you go ahead and you find out, if we take that and put it in the calculator, what value does it approach? It will get closer and closer to this value of E. So do you remember what that decimal version was? Well, it's 2.718, which is usually where we stop. But then it keeps on going because it's kind of like pi. It goes on forever, ... So we're going to stop right here at this 2.718, okay? Now, again, this is definitely when you want to use a calculator to make your life a lot easier. We're never going to make you do an E function by hand, okay? Unless we are going to get really, really lenient about it. All right. So if we notice both of these, which is going to be important to know what's growth and what's decay. okay? If you have an e to the x, if your x is positive, that's growth, and if your x is negative, that's decay. So this is 3, so we would go ahead and say, notice there's no k, so my asymptote is at 0, my crucial point's out 0, 1, and then because it's growth, I'm going to go over 1, up 3. Boom. Super easy once we do this by hand. I crossed my asymptote, we'll go ahead and do that. So if we do e to the x, we're going to get some fun values, so we might as well just throw that into your calculator. If you look at the divide sign, you're going to see a lowercase e. Boom, that's our e that we're going to be using, our natural base. E to the x, and then I'm going to go ahead and hit table. You can see all your values right there. So 0, 1, again, that common point, and then 2.718. It's going to look very similar, okay? But it's just not going to get as big as fast. So for both of these, our domain is -infinity to infinity, and our range is going to be from 0 to infinity, or y is greater than 0. Alrighty. So just like any other function, we can move it. So this is still our asymptote at 1. Boom, 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 boom. Our critical point is right there, but because of our asymptote, we'll move it over 1. We have a +3, so we're going to go opposite to that. So right 3, 1, 2, 3. So this is our actual critical point now. I'll put that in green so we can see it. And then because it's e, again, that's 2.718, which is almost 3. You're going to go over 1, up 1, 2, 2.78. Boom, shakalaka, there you go. So even though we shifted, our domain is still from -infinity to infinity, and our range is going to be from 1 to infinity. So notice we're getting a little bit faster with this because it is a little bit easier and you don't need the table. Alrighty. So let's finish up today with some interest examples. So we have two formulas for compound interest, or money you make when you invest stuff. The first one is known as PERT, and that's for continuous compounding. Please circle the word continuous, because we're going to use it continuously, so we need to use or look for the word continuous or continuously. Every other time, we're going to use this one, which is the R over NT. T is always in years. Ours is going to be a rate. This is where we're going to make mistakes, sports fans, so let's write this down. This needs to be converted to a decimal. Alrighty, and then N is going to be your compounded times per year, and that's what all this other stuff is. So if it's compounded annually, your N will be 1, quarterly is 4, daily 365, weeks would be 52, and then semi-annually is 2. Goodness gracious. Now there's also monthly, which is 12, so on and so forth. Okay? So this P in both spots, though, is going to be your initial amount. So let's go ahead and put initial $sign there. Dollar bills, y'all, because that's what your P is going to be. So JC deposits $400. So we're going to start with the 400. And then before we get too crazy, we need to know what we're compounding. Is it continuously or is there an amount? So it says monthly. So because it says monthly, I now know I'm going to use that equation right there. So 1 plus my rate, which is 7%, 0.07, is that as a decimal. Monthly is 12 to the 12 times 10 years. Notice it's RNT, so we're going to multiply those together. Cool? Alrighty, so you can do this step by step. You can put it all into your calculator, but parentheses stake, I should do that first. So 400, 1.00583 to the 120, and then we plug that into the calculator, and we're going to go ahead and get $800. That's not an 8. 3.86. Now I tell, technically it's 8645507, but I put that in red because the bank is not going to give you that money until you've earned your cent. You ain't getting it. They'll keep it. They'll look at it, but they're not going to give you an actual decimal fraction cent. So let's keep things in terms of cents to make things easier. All right. So let's look at the next one. It says Zachary or Zach. It's going to do the same $400 compounded daily. So again, we're going to be using that equation. So 400, 1 plus 7%, 0.07, 365, and then 10 years. So like I said initially, you can do this by hand or plug it in the calculator. So let's show you how to do that on the calculator. So let's get out of the grapher. So 400, and then parentheses, 1 plus 0.07 divided by 365. Hit the caret button to go up to making an exponent. 365 times 10. And we're going to get 805.44, and then I'm going to stop there. Notice my calculator gives me some fractional cents. Well, the bank's not giving me that. Let's keep this a real-life example, so let's keep it right there. Cool? All righty, ladies and gentlemen, we are almost done here. Let's go to this next part, and we'll do this super quickly. So in this example, we're just trying to tell you, hey, if you look at all these different times, what are we looking at? What happens? Okay, so we're going to say you have 6%, $200, 20 years. So annually would be 1, quarterly is 4, monthly is 12, continuously means we're going to use our E equation. So we're going to finally use PERT. So what we're going to notice is that you go 200, 1 plus 0.06 divided by 1 to the 1 times 20. And then 200, 1 plus 0.064, 4 times 20. We're just plugging in all these different equations here. And then finally, we'll use PERT, e to the rate, 0.06 times 20. So that one looked a little bit different. Okay. Notice here, for these ones, we use P1 plus R over N to the NT. And then once we got down to continuously, we use the PERT equation. Okay. So I like PERT, 1, because we're going to find out it gives you a lot more money, and 2, it's easier. So if we plug all this in the calculator, let me just jump straight to the answer because this has been a long video, as we've seen already. We're going to go ahead and have 64.42, 60. Clearly I did something wrong there. Let's just skip that anyways and do 13,66204, 66402. And as we can see here, ladies and gentlemen, as we're going, the compound interest gets greater when your N gets larger. Because look at all this money you're making. More money. So when they say how much you're compounding it when you're investing, ask them. Say, hey, when are you compounding this? When am I getting paid? Am I getting paid monthly? Am I going to get paid quarterly? Is it annually? The bank's going to try to do annually because they don't want to give you as much money. You say, hey, can we do it continuously? So you're always making more money, and that way you're going to make the most money. So ladies and gentlemen, boys and girls, that's going to be it for today. Hopefully you have a wonderful day, and we will check you next time.